Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Scott Dodelson, who is Professor of Physics at Carnegie Mellon University. He serves as co-chair of the Science Committee for the Dark Energy Survey and is actively involved in the LSST Dark Energy Science Collaboration and work with data from the South Pole Telescope. Welcome, Scott.
Hi, nice to talk to you.
Yeah, thanks for doing this. So I want to start with it's called the Building for Discovery Strategic Plan for U.S. Particle Physics in the Global Context. And you were part of the committee that put out this report a few years ago. And in the report, you say particle physics explores the fundamental constituents of matter and energy. It reveals the profound connections underlying everything we see, including the smallest and the largest structures in the universe. And the field has been highly successful. Investments into this field led to many things that we can remember in the last 6, 7, 8 years. Discoveries of the heaviest elementary particle, the top quark, the tiny masses of neutrinos, the accelerated expansion of the universe, and the Higgs boson at the Large Hadron Collider. You say current opportunities will exploit these and other discoveries to push the frontiers of science into new territory at the highest energies and the earliest times imaginable. So there is a lot to explore there, Scott, but obviously there is always a resource constraint and budgetary constraint. So part of this report is looking at what could be the priority items for the U.S. to think about, right?
That's right, yeah.
So you want to talk a bit about that?
Yeah, sure. So that committee was, I think, one of the most fascinating things I've done. It was the end of a year-long process where about 1,000 members of the community got together in a series of meetings trying to prioritize what the community should come together and build. And just to give you a sense of scale, roughly speaking, the budget is about $1 billion per year. So as you point out, that's not infinity. So that means you can't do everything. And in addition, the biggest machine for this type of field is located in Switzerland, as you mentioned, at the Large Hadron Collider. So to some extent, at that time, 2013 or so, the field was in a bit of a crisis. People wanted to do their own thing, and it wasn't clear whether we would come together. And so the whole community came together, and then from that 1,000 people, there was a group of 20 or so people, some really smart people, Nobel laureates, and then I was there also. And it was just fascinating listening to all these people trying to figure out this problem. And that report, it's called the P5, the Particle Physics Project Prioritization Project. That report was delivered to Congress, and it's been tremendously successful in the sense that the funding, because the community came together and supported this, like 2,500 people signed the report. The Congress has and the administrations have been very, very supportive, funding things beyond what we expected even. So in that sense, just logistically, it was tremendously successful, I think.
Yeah. So the Large Hadron Collider, the LHC, as you mentioned, in Switzerland near Geneva, before that was constructed, in the US, what we had was a Fermi.
That's right.
Um, okay.
At Fermi Lab is a lab in Illinois, where I used to work, and they had the biggest collider. They discovered the top quark there. But these machines are tremendously expensive, and really requires a world effort to construct one. And the Large Hadron Collider is roughly a $10 billion machine. So and the next one's going to be a factor of 10 more expensive, maybe. So there was just no way we could have envisioned taking the leadership in that field from them, which made the problem particularly difficult.
Right. Yeah, I know that, the Higgs boson was a very exciting discovery out of the LHC. But more recently, Scott, obviously I'm not an expert at this, there has been a lot of experiments looking for additional particles or additional discoveries, but many of them sort of came out empty, right?
That's right. So one of the kind of ironic things about particle physics is it has been so successful, and if you think about it, it's really a millennial. It's an endeavor that's been going on for thousands of years, figuring out what things are made of, and we've been able to get down to the level of atoms. So we now know that everything, you, I, the table, the desk, the chairs, the plants, are made of just fundamental atoms. We know there's 100 or so elements, and each of those elements is only made up of a few fundamental quantities: protons, neutrons, and electrons. So that is a huge advance. Think about 1,000 years ago or 2,000 years ago. And now we've been able to look inside of protons and neutrons and discover the existence of quarks and a few other elementary particles. But we kind of have it cleaned up. We kind of basically have a table that lists the fundamental particles. There's not that many of them. We've measured everything about them, and everything is right. So that's a great success, but it leads to the question that you asked, which is, where do we go from here? Can we expect to find new things or not? And people were hoping we would, and as you pointed out, so far we have not.
Right. And so the very highest level for the entire universe, about 14 billion years old, when we look at the entire universe, the things that we can see, the atoms, the molecules, everything that we can see, the stars, the planets, is only about 5% of the universe, right? And so there are two hypothesized things. One is called dark matter, which is about, how much is it? About 25%. And then the other component is what's called dark energy. So both of these things are sort of puzzling, and we've been looking for them, but it's a really big part of the universe, right? So it's sort of, we understand pretty well the 5%, but the 95% is out there that we don't quite understand yet.
Yeah, I think that's an area that has given people hope. In particular, the dark matter problem, people feel that it's amenable to discovery at things like the LHC. So there's a connection between these big machines and cosmology. It's kind of an interesting connection, and it relies on something that's not obvious, or at least wasn't to me, and that is that as you propel these particles to higher and higher energy, what you're actually doing is looking at smaller and smaller subdivisions of them. So if you think about that, then to look at the smallest possible part of the things that, inside protons and neutrons, or new stuff that might be there found at the LHC at even smaller scales, you actually need ridiculously large energies. The only time those energies were ever around, except for at the LHC, was in the very early universe. So that kind of cements the connection between cosmology and particle physics. And this report that we came out really did prioritize quite a few cosmology projects, which is kind of strange to some extent. Why are people who are interested in the fundamental constituents of matter, why are they building telescopes to look at the universe at large? But it's built around this connection, really.
Yeah, so what's the status now? I know that there was some conversation around a bigger accelerator, perhaps in Japan, bigger than the LHC. It seems to have not really going forward, right? So is the idea now to sort of power up LHC to a higher level or look for a bigger one?
Yeah, I think the thing that is going to happen and will be the basis of the field for the next 15 years or so is the LHC is going to increase its luminosity, the number of particles it shoots around per second. And that has the possibility of turning up new physics, as you proposed. The question of what will succeed the LHC is, as you said, Japan had a proposal. We're not sure if that's going to happen. China's also interested. My sense is the whole world's going to have to come together and get behind this. And my other sense is I'm not sure we're going to get it funded if we don't believe that we're going to discover something. We can't just say we want $100 billion to build a machine because we think we want to see what's out there. There's a better reason for that scale of money.
Yeah. I mean, 100 billion. Yeah, although it sounds big, we are now thinking about trillions of dollars in propping up economies. And so like you say, it has to be a global endeavor. And I know that in the political sense, last few years have been, taking a step backward in terms of sort of universal collaboration and doing things together. Do those things have got filtered into the scientific arenas too?
Not at my level. In the sense, I'm part of a large collaboration of about 500 people called the Dark Energy Survey, and I talk, every day to people from Brazil, Australia, Germany, England, and a few other countries, and it's just wonderful. It's a great opportunity. I've been so privileged to meet people from these countries and to explore different lifestyles. It's just been such a wonderful opportunity for me. And we're all consider ourselves equal. There's no vying for my country's better than your country. So at my level, at least, it's been great. What happens at much higher levels, I can't really speak to. I mean, I actually think the government has done. There are the civil servants within the government who are around throughout as administrations change, and Congress as well. Congress has been very supportive of these international efforts, which is great. And the civil servants in the Department of Energy, for example, are just terrific at maintaining these international collaborations, for example, at the Large Hadron Collider. So the U.S. is the biggest participant there. So I think things are actually going fairly well in terms of these international collaborations.
That's excellent. Yeah. And so strategically for the U.S., LHC is going to be over there in Switzerland. There is, sort of a power limitation at Fermi. And neutrino is something that fits into a lot of those puzzles, right? I think it is too light to actually make up for the dark matter. But there are a lot of interesting questions around neutrinos, right? Is that something that the U.S. is sort of taking a lead on?
Yeah, exactly. So that's what this P5 panel proposed to kind of solve the conundrum, which was it's possible to learn about the properties of neutrinos. The neutrinos are these very mysterious particles that are much, much, much lighter than electrons or protons and neutrons for sure. And so one of the really kind of mysteries we'd like to understand is why are they so light? And so the idea is that, and the other weird thing about neutrinos is they're kind of very ghostly. They don't really interact with things. So actually, as we speak, there are quadrillion neutrinos passing through your hand. You just don't feel them. Right. And they were produced in the very early universe. So if you could actually catch one, you'd win a Nobel Prize. But it's very hard. You have to build huge detectors to even see a few of these neutrinos interacting. So that's what Fermilab is doing. They're building a huge beam of neutrinos. They're going to shoot it underground to South Dakota and build big detectors there and try to study the properties of these neutrinos. So that was our compromise result. Yeah, and fascinating. Another fascinating thing about neutrinos, they come in different varieties, right? And they seem to be able to go back and forth without any real logic behind them. Yeah, that's right. So that's a function of quantum mechanics that you can have one neutrino. There are three types of neutrinos, as you said, and one type can actually, as it's traveling, just transform itself into another type. And that's one of the key things that this experiment that is currently being funded in Fermilab at South Dakota is aiming to study are these, we call them oscillations from one type to another. Learning about those will help us learn about the masses of neutrinos and other properties of them.
And so my understanding is that is not really going to resolve the dark matter puzzle, right? We are still looking for other things to.
Yeah. Right. I think that's probably right, with the caveat, and that is that right now there are 3 neutrinos that have been discovered. There's also the possibility that there's an even more ghostly set called sterile neutrinos that interact even more weakly with ordinary stuff. And it's true that the normal 3 neutrinos can probably not be the dark matter, but one of these sterile neutrinos, if they exist, we don't even know if they exist. If they did, one of them could actually be the dark matter. So it's
because they're heavy.
We don't know if they exist. So we don't know what their masses are. But if their masses were right, then they could be. And in fact, there's been some hints that they do exist. Because if they did exist, one thing they would do is they would out in space, there would be a bunch of them. There's a lot of dark matter out there, and from every once in a while, they would decay into a regular neutrino and light and photons. So we can actually potentially observe light coming from, say, the centers of galaxies or stuff like that to see if we can see this signature of photons coming from neutrino decays. And there's been some evidence that we do see something like that. So it's not a crazy idea, but it's certainly not. Most people wouldn't call it the front runner for dark matter.
Right. Yeah, it's sort of a strange thing, right? Do they actually derive their mass from the Higgs field, or they're sort of completely independent?
You mean the sterile neutrinos or the ordinary?
Or even the regular neutrinos?
That's a very good question that we don't know the answer to. One possibility is they do derive from the ordinary Higgs field, just like other particles. If that were true, it's very, what we call technically unnatural. It would require numbers in the fundamental theory to be absurdly small, like 1 part in a billion or something, which just seems kind of crazy to most people. So there's another way of doing it that invokes not just the Higgs field, but a much heavier particle that we could never see, that would give these neutrinos light masses through some kind of more natural mechanism. So you can kind of see where we're floating around in the dark for figuring out why these neutrinos are so light. We've come up with ideas. The person who came up with that idea was Murray Gell-Mann, who won a Nobel Prize for something else. So, I mean, these are deep questions that we're trying to work our way through. Yeah.
Okay. And so what did the report, what priority did it come up with? In other words, if you had that $1 billion budget, there is dark matter, there's dark energy, there are questions around inflation, cosmology. We talked about neutrinos. There could be new particles and other interactions. How would you allocate that constrained budget?
Yeah, I mean, we actually did it with spreadsheets. I mean, we asked each project to present and tell us how much it would cost, and they gave us 3 budget scenarios, and we worked through it and we made proposals. So it was a very concrete committee, and they listened to the committee over the past, I guess it's been about 7 years since then. And they've made every project that we proposed happen. So it's been, in that sense, it's been successful. And one of the things I was most proud of is, it's true we supported this neutrino experiment, and that's interesting, but we also supported them investing quite a bit in cosmology experiments. I work in cosmology, and I think it's really an exciting field. So there are a number of cosmology experiments that are going to happen, and there'll be big experiments that can only be funded by the government, and I think it's a good role for the government to have. So I'm pretty proud of that. It's a good way to help young people learn very technical issues and maybe propagate that out into society. It's a way to make great discoveries for which our civilization will become known. So I'm pretty happy with the way that whole thing turned out.
Yeah. So Scott, this is sort of my. I don't know much about this, but from afar, if I look to the field, it seems like we need LHC-like machines that are extremely expensive, and telescopes and other types of things, satellites. So the engineering direction is really expensive. Are we? Let me ask you this, and you can tell me if it's yes or no. sort of not paying enough attention to the theoretical aspects. Since quantum mechanics, say for string theory, which is sort of out there, we don't seem to have made a lot of advances on the theoretical arena. Is there a reason for that?
Yeah, I think so. I mean, I think the reason we haven't made advances with at least connecting the theory to the experiments, because you cannot test a theory like string theory with any kind of a reasonable budget. So the people who are doing, and this to some extent speaks to not only a problem for theoretical high particle physicists, but for the whole field. That is, eventually we'll be priced out of the field, right? When that's going to happen, no one knows, but it's going to happen because it just become too hard to, build the next generation of colliders. And one of the things that I find interesting is that these theorists are quite, they're quite resourceful. So what people who used to think about things like, the dark matter or what they'll find at the LHC have kind of pivoted a little bit. And now they're thinking about completely different things. For example, they're thinking about what's been called the second quantum revolution, which is that about 20 years or so ago, people discovered that when you just look at a single layer of atoms in such a two-dimensional system, basically, the laws of quantum mechanics are behave completely differently. So there's all this new physics that people are discovering that will likely power the next generation of devices, such as quantum computers and quantum sensors and stuff. So understanding those systems is proven to be extremely challenging and a really good fit for the tools that high particle physicists have developed. So I think that's one of the exciting developments, is that we understood kind of the challenge that you presented to me, that what are you going to do if you don't see anything, and a lot of theorists at least are pivoting to that, to new applications.
Yeah, that is really really interesting. So the two-dimensional matrix of materials, some of them could be superconducting, right, in that room temperature.
Yeah, that's another possible application. Yeah.
Yeah, so if you find those applications and the field really takes off, that connection, if physics can make that connection, then it's self-funding, right? It accelerates from that point on. So that seems like a very interesting direction for the field.
Yeah, and as I said, it is something for which it's complicated enough that the full set of tools that particle physicists have developed are potentially quite useful. And in fact, it goes the other way also. When we start thinking about building these quantum devices, they're called, it's possible that they can help us detect the dark matter. So a lot of people have been working, the DOE in particular has been funding ideas, kind of blue sky ideas for building new detectors based on these new quantum devices. So that's a way that we'll come full circle and not only contribute to our understanding of quantum mechanics in these new systems, but use the systems to learn about, for example, dark matter.
So from your perspective, Scott, how far are we from sort of a practical quantum computer? I know that Google demonstrated something recently with a dozen qubits or so, maybe a couple of dozen qubits. So where are we in terms of a real practical quantum computer?
Yeah, here's where I'm falling off the edge of my limits of knowledge. But one thing, I'd say there are about a half a dozen possible categories of what will eventually be a quantum computer. I'm 100%, I'm quite optimistic that eventually we'll get there, human ingenuity being what it is. But exactly which technology will get us there is unclear. Right now, there seems to be a race in industry to say, oh, I had 20 or 40 or 60 qubits, and if you have the most, you win. But that's probably not going to be the technology that gets us there. So one thing we're looking at is the idea of topological quantum devices for quantum computing. So these are things that have kind of a protected quantum number that can't get changed by little blips and stuff. And those things might be particularly stable for qubits, which is something you need in a qubit. So that's something that we're kind of considering. But if in 10 to 20 years, which technology will win, I don't know. I'm not sure anyone knows really. Yeah.
Yeah, so that's interesting. So that you're saying there could be sort of different technology directions to get there. So the topological material that is the same as the two-dimensional
For the
material that you
most
talked about?
part, yeah, those seem to be the most promising. There are also these topological insulators that are three-dimensional, but it's a strong overlap between those two sets of things, I think. Yeah.
Okay, yeah. So there appears to be a lot of opportunities in the material
Yeah.
sciences arena. Sounds like, right? And it's a sort of theory and engineering coming together again to potentially make
Yeah,
a
and
big jump
it's
in
more than
terms of,
just that.
yeah,
It's also, think of all the computer scientists with the algorithms for quantum computers. It's the whole new, that itself is a whole
right.
new um, set of people who are getting involved in this game. So the whole field is emerging to be one that brings together people with a wide range of skills and tools. So it's quite an interesting field. I actually love to get involved in it, but haven't had the chance really to get that immersed in it. Yeah.
Yeah, what's exciting is, so that is on the supply side, but there is a big pull from the demand side in terms of artificial intelligence, in terms of capacity needed, right? And so all these things are sort of pointing toward a potential technology breakthrough that could get us
Yeah,
to the
and I
next
think
level.
I guess I think of those two things as two. I mean, I'm sure you do too, as two different things: a quantum computer and artificial
Yeah.
intelligence. And I guess I would have thought one of the first applications of quantum computing would be in the security area. Um, but
Oh,
but I guess you're right that in principle it might help speed up some artificial intelligence calculations as well. Right now, I'm not sure speed is so much. Well, I guess it's hard to know whether speed is a limitation there.
yeah. I think it will be in a very, sort of specific industries like pharmaceuticals, high throughput screening, designing a product like a vaccine, things like that. I think there is still some sort of technology constraint there in terms of, just running a sheer number of experiments in a very
Yeah,
fast fashion. But we are probably far away from practical applications. We'll take a quick break, Scott, and when we come back, we'll talk about the
sure.
dark energy survey. Thank you. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. And so we are back. Scott, you've been intimately involved in this dark energy survey that has been going on. And it's sort of focused on so the data that is in between its predecessor, which is a Sloan digital survey, as well as a South Pole telescope. And it's looking at very large number of galaxies, I guess, right? So could you talk a bit about the technology being used and what the objectives are of the dark energy survey?
Yeah. So the camera was built at Fermilab, and
Yeah.
it was then moved to a 4-meter telescope in Chile. And it took data for about 6 years, starting in 2013. So we're done now with the data, and we spent the years from 2014 to 2017 analyzing just the first year of data. That took us 3 years, and we put out results that were pretty interesting. And now, just today, we reached kind of a milestone in our second phase of analysis of the first 3 years of data. So I'd like to try to convey the excitement around that. But
Yeah.
in order to do that, I have to kind of give the backstory, if that's okay.
Sure. Yeah, absolutely.
And in a word, what we're trying to do is test the current canonical model of the universe, which you kind of outlined at the beginning of our discussion, that the canonical model is that the universe is the energy density in the universe is made up of 25% of dark matter and about 70% of something called dark energy. And the most common form of dark energy that is assumed is something called a cosmological constant, the energy associated with just empty space. So that's the model in a nutshell. And
so that is what's called lambda CDM.
Exactly.
Yeah. Okay.
And what we're trying to do is test that model.
Yeah.
So that's really my goal, is to disprove it, because I think it's absurd to invent two new things and just make it up. So that's my goal, to do that. But everyone has their own goals and stuff. So
yeah.
In order to do that, we're doing the following test. So the cosmic microwave background, which has been measured many times, for example, by instruments at the South Pole, that gives us a picture of what the universe looked like when it was very young. And that picture reveals a surprisingly homogeneous universe, where the density is very close to the same everywhere you look. Today, that's not true at all. Today, the universe is very inhomogeneous.
Right.
So what lambda CDM, this model that you mentioned, does is it gives actually a prediction quantitatively for how inhomogeneous the universe should become over time. We know how it happens. Small overdense regions gradually accrete more and more matter due to gravity. But the precise rate at which those regions grow is dictated by that theory. So given the measurements of the cosmic microwave background, you can predict exactly how inhomogeneous the universe should be today. And we roughly measure the universe today in this dark energy survey. So one way to think about this in a metaphor is, think back to the United States in 1790. There were 50 people per square mile in New York City. Today there are 50,000 people per square mile. So how did that inhomogeneity grow over time? There are a bunch of forces, social and political and economic forces that led to that growth. If you had a theory that actually predicted that exactly, that would be incredible. And that's essentially what we have for the whole universe. We have a theory, this lambda CDM, that predicts exactly how inhomogeneous the universe should be when we measure it in the dark energy survey.
But the prediction would be a function of the lambda, the value of the lambda, I would imagine, right?
A little bit, but that's pretty easy to pin down by other means.
Okay.
So actually, it's a good point you make, that you might think, maybe the prediction you can change if you change some of the parameters. There are a few parameters you can tweak. But actually, there's very little freedom left after you measure the microwave background. So it's close to a zero parameter prediction. So that's kind of exciting, because it gives us something to hit at. It's just a target out there to try to go after, to see whether we get the right answer. And by the way, if we do get the same answer, it's remarkable that two completely different instruments measuring two different completely things separated by 13 billion years could be connected at the few percent level. That is a remarkable achievement, I think.
Mm-hmm.
So anyway, we're in the process of hitting hard on that model, lambda CDM. And what we do to protect ourselves against unconscious bias is we blind the data. So what that means is, as we're developing all of our analysis tools, 100 or so people over the course of 3 years, we don't look at the data at all. We only use the tools on simulated data. And we test that, and we try to make sure we don't have any bugs in the code and stuff like that. And only at the very end, when we're sure we have it right, do we unblind ourselves and look at the data. So today was actually the day we unblinded the data. So it's been kind of a crazy day, because for the first time, 120 of us were on this Zoom call. Google Sheet stopped us from editing because there were so many people editing at once. So it's just been a chaotic day for us, and we're hoping to make sense of all this and get it out to the public within the next few weeks or a month or so.
Wow. Yeah, I mean, it's so exciting, right? Because you've been waiting for it. So how much was it? 6 years of data collection?
That's right. Yeah.
And then, sort of 3 years of analysis now, right, of that data.
Yeah.
And there are a lot of objectives, right? So clearly, really understanding that lambda and dark energy is one of the objectives. But this also gives you a lot of other ideas, right? So you talk about weak lensing in here. So what exactly is weak lensing?
Right. So actually, that's the way the tool we're using. It's this idea of gravitational lensing, or weak gravitational lensing, is something that Einstein kind of came up with, but he missed the boat on this one. So the simplest manifestation of lensing is if you have a light ray, it gets bent as it passes by a massive object. So if you can imagine this in your mind, if you have a big star, say, behind a big mass, along the same line of sight to you is another big thing in between us and the star. The light from that star will get focused on us from all directions. So what we'll end up seeing is kind of the star will not appear like a point thing. It will appear like a ring around the massive lens. So that's called an Einstein ring. Einstein only wrote about it in the 1930s. And the reason he wrote about it because a busboy in Washington, D.C. did the calculation and in Einstein's theory, and he submitted it to Science magazine that they would be this thing. And the editors of the journal said, no, we can't publish this because we don't know who you are. So he traveled to Princeton and asked Einstein to publish it. And the first letter of the first sentence of the letter that Einstein published was, this person, I forgot his name, asked me to publish this letter even though I don't think it's important. So this whole phenomenon of gravitational lensing that Einstein's theory predicts, Einstein himself never thought it would be observed, but over the past 30 years or so, we've observed it. In particular, the way we use it is we look at the shapes of galaxies that are very far away, and we see how they've been slightly distorted by the intervening matter. And by doing complicated things, we can figure out how much matter there is in between us and those background distorted galaxies.
And that matter is dark matter or something else?
It could be both. I mean, gravity doesn't care what your color is.
Yeah.
It can be dark matter or ordinary matter. I mean, sometimes people call the maps that are created from gravitational lensing dark matter maps because, as you said, most of the matter probably is dark matter. But the fact is, all matter deflects light.
And so this is actually looking at the galaxy itself. It's not an object. So you're looking at the shape of the galaxy.
That's right.
And really looking at what distortions you could see, right?
But it's not. It's not just one galaxy. It's 100. It's 100 million galaxies in the dark.
100 million galaxies. And so clearly, the amount of data coming out of this experiment is quite amazing. So. Is much of this analysis sort of automated? How does it work? First of all, what type of data? What's the amount of data we are looking at?
Yeah, that's a good question. How big are the files? So
I know that's 500 megapixel or something. Is kind of the one shot.
Yeah, I mean, the data goes through various stages of reduction. The raw data is so big that I've never seen it. The biggest files I've seen are kind of reduced images. And those are at the petabyte level, I'd say.
Okay. But the scope here is hundreds of millions of galaxies, and so lambda. So is one of the objectives here to pin down lambda more precisely?
I don't think so. I think the prime objective is really to figure out whether that is. Whether that model lambda CDM is correct, and in particular whether what's really dominating the energy of the universe is this cosmological constant. The exact value of it, if it exists, is not that important. What's more important is whether that's what's doing the job or not.
Okay. So the objective is actually much bigger, which is, like you said, is to either reject the status quo theory or to accept
Exactly. And coming back to something you said a half hour or so ago, when this whole notion of dark energy was first introduced, there were literally 1,000 papers written about ideas for what dark energy could be. And after a while, the best theorists, I think, started to lose interest in this because, there's just 1,000 things. And so how are you going to distinguish them? So a lot of us have kind of turned to looking at the data to see, and I think our first goal is really to hit on this, the one model that seems to be the simplest that everyone seems to hit upon, this lambda CDM model, to see if this is right. If it's not, then the floodgates opens again for the theorists to come, join the room. But right now, we really want to just try to stress test this model.
So if you were to reject lambda CDM, then it will have implications. CDM is starting at about 380,000 years, right, from the start. So it would have implications for inflation and everything else, right, going backward.
Not necessarily. I mean, it's possible to replace. So I guess one way to think about it is you alluded to inflation, which is a theory that is that in the very, very early universe, something interesting happened when the universe was a fraction of a second old. Then dark matter, as you say, kind of plays a very important role when the universe was a few 100,000 years old. In particular, it helps the these inhomogeneities grow to be as large as they are today. And dark energy is something that's just emerged over the past few billion years or so. So dark matter is still around today, but in terms of cosmological evolution, those three substances are kind of three different epochs. So if we, take out lambda as the dark energy and put in something else, it doesn't necessarily impact the correctness or the existence of those other two substances.
Okay. So the inflationary phase that we are in now, that's sort of exponentially increasing too, right? It's sort of a runaway expansion of the universe.
That's right. So you use the word inflation twice in the last two sentences. One is alluding to some epoch where the universe, we think the universe accelerated very rapidly in the first fraction of a second. That's canonically called inflation. And the epoch of acceleration, today we've observed the universe apparently is accelerating also. And people don't usually call that inflation, but that's what it is, really. It's the universe expanding exponentially rapidly. And wouldn't it be nice if there was a way of tying those two periods of acceleration together? And it turns out there are, 100 papers that do that, but none of them are particularly compelling. So we're just trying to do what we can to, explore this particular epoch of acceleration. Yeah.
Okay. So is the experiment completely done? The 6 years of data, you're not collecting any more data?
Collecting the data, yeah.
And so this instrument is mounted on a telescope in Chile. So that will then go back to some other new experiment that you will design? What happens?
So that's a 4-meter telescope. It's useful for many reasons, many objectives. But one thing we talked a little bit last time about the Department of Energy's facilities. So the National Science Foundation also has facilities, and they're also constantly prioritizing them and trying to figure out what will lead to the most discoveries in the future. So 4-meter telescopes are probably not going to be at the forefront of discovery, or at least not the biggest discoveries over the next decades or two. So, they're thinking about 8-meter, even 30-meter telescopes that might power the next generation of surveys.
Yeah, so it's an exciting time for you. So Scott, I want to ask you in conclusion, going back to the particle science strategy report. If you had infinite budget, based on everything that you know, where would you put the biggest focus on? Whether it's a new type of experiment or theory, or we talked about topological materials, we talked about material science, quantum computing. Where do you think you will put sort of the biggest priority on?
It's an impossible question. I think in terms of cosmology, I think we're kind of reaching the stage where particle physics, we're maybe 10 years behind them, that I'm not sure you can justify building another $1 billion experiment. There'll be a few coming up over the next decade or so. After that, I'm not sure if we're going to be able to justify that. So thinking in one of these upcoming fields like quantum science or biophysics, or maybe cosmology might have something by looking at neutral hydrogen called 21 centimeter experiments. There's a couple of options for really big experiments. Plasma physics seems like it's becoming potentially interesting in the US again. So it's the kind of thing that requires the study that we underwent 6 or 7 years ago, where you bring 1,000 people in, you listen to them carefully, you put a bunch of smart people in the room, and you try to prioritize it. That's something that from that experience, by the way, we did no voting there. We just came to consensus just based, if someone disagreed, we had amazing. Just discussions. And it was just remarkable how rational people could come together, even starting from very different starting points, and agree based on, arguments that were convincing.
Yeah, I mean, that's what happens if you use science, logic, and information to reach a conclusion.
Yeah, I think it's
not just opinions.
Yeah, it made a huge impact on me. That's why I've tried to, run whatever I run now, and it's just so. And as we know in society, it seems increasingly difficult to do, but it seems like a goal to aspire to.
Yeah, I want to ask you one other question, Scott. I remember reading, and I always thought about this. So LHC, just the scale of it is enormous and obviously big investment, like you said, 10 billion. There was something out of Berkeley a few years ago that sort of went the direction of sort of a desktop um, accelerator. So is there a direction of miniaturizing these experiments in any ways? That's not possible
Yeah, I
at all.
think Berkeley, and actually the person who was involved in that was on this committee.
Yeah.
There are these plasma Wakefield accelerators and other ideas for getting the same bang for the for getting making them much smaller, miniaturizing them, and doing it in very clever ways. So far, they haven't panned out, but we advocated investing in these ideas. They don't require that much money, so it's an interesting class of ideas that might emerge at some point in the future. Yeah.
Right. Excellent. Yeah, this has been great, Scott. Thanks so much for spending time
Nice
with
to
me.
talk to you, Gil. All right, take care.
Thank
Bye-bye.
you. You too. Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.